Good morning, students. Today we are going to see the factors affecting the magnitude of delta O or 10 dq. In last lecture, we see the evidences for 10 dq or delta O. That 10 dq or delta O is affected by the various factors. We are going to see that particularly factors that magnitude of 10 dq or delta O in an octahedral complex depends on first nature of ligand, second charge on metal ion, and third one is the position of transition metal element in the first, second or third transition series in the periodic table. We discuss these three factors one by one. First, nature of ligand. See in this particularly table, this gives the variation of 10 dq or delta O values when the ligand will be changed. Where we see the complex of the chromium with different ligands. See first CrCl6 3 minus, CrH2O6 3 plus, CrNH3 6 3 plus, CrCN6 3 minus. In these four complexes, metal ion is the same, but ligands will be get changed. And as the ligands will be get changed, see their absorption peak will be get having the different values. See absorption, first chloro complex gives the 13,640 centimeter inverse. Delta O in kilojoule, it is 163 kilojoule mole inverse. For the echo complex, see 17,830 centimeter inverse. Its 10 dq in kilojoule is 213 kilojoule mole inverse. Amine complex, it is 21,680 centimeter inverse. Its delta O in kilojoule 259 kilojoule mole inverse. And third, cyanide complex of chromium shows 26,280 centimeter inverse. Its 10 delta O or 10 dq in kilojoule mole inverse is 314. It follows that the value of 10 dq or delta O increase with increase in the strength of the ligand. Thus, the sign gives that the splitting is more by the strong ligand, while chloride produces the less splitting, while cyanide produces the large splitting, and thus cyanide is the more stronger while chloride is the weak ligand. This is on the basis of spectrochemical series. Second factor, charge on the metal ion. As CFT is based on the electrostatic model, the charge on the metal ion has a direct effect on the magnitude of 10 dq. Different charges on the same metal ion. See, a metal ion with the high charge attract the ligands more close and therefore produces the more splitting than the ion with the less charge. For example, see here, metal atom and the ligands are the same, only difference in the charge. For example, there are two complexes, CrH2O6 2 plus and CrH2O6 3 plus. See, the complex or the metal complex with the Cr2 plus, it has the 10 dq value 39.7 kilocalories mole inverse, and the second complex which having the Cr3 plus, its 10 dq is 560.94 kilocalories mole inverse. Thus, higher the charge on the metal can polarize the ligand more effectively, and so the ligand can approach more closely to the metal ion, which will be results in the greater splitting, that is higher is the 10 dq. That means lower is the charge, lower is the 10 dq, higher is the charge, higher is the 10 dq value. Second, different charges on the cation on the different metals. In this type, if two different partners with the same electronic configuration and the same geometry of the complex are chosen, then it has been observed that cations with the higher charge has the higher delta O or 10 dq. For example, vanadium 2 plus and chromium 3 plus. Vanadium aqua complex Fe2O6 2 plus shows the 10 dq 12,460 centimeter inverse, which have the D3 system, and CrH2O6 3 plus, its delta O is 17,400 centimeter inverse. Cr3 plus, here it have the 3D system also. Thus, higher the charge on Cr ion than vanadium 3 plus ion, it can polarize the ligands more effectively, and so that the ligand can approach more closely to the Cr3 plus ion, which will be results in the greater splitting. That means the higher 10 dq value for the complex of Cr3 plus. Third factor, same charge on cation with different electron configuration. Though the charge on the metal complex is the same, but their electron configuration is different. At that time, we having the two examples, that is COH2O6 2 plus and NiH2O6 2 plus, both metal ions in 2 plus charge, but their electronic configuration is the different, which one have the D7 system and another having the D8 system. See, the CO complex have the 10 dq value 9,300 centimeter inverse, while the nickel complex have the 10 dq 8,500 centimeter inverse. That means here there is the unpaired electrons or the electronic configuration will be changed, and it can show the higher values. Third, the row in which the transition metal is placed, that is the position of transition metal elements either in first, second or the third transition series. See, we are having the three examples with the same ligand. From first row, cobalt is the metal, from second row, rhodium is the metal, and from third row, iridium is the metal atom. They have the complex with the NH3 amine ligands, and all having the same charge, same oxidation state and same ligand, but their 10 dq value is the different. See, CO NH36, it have the delta O at delta O 23,000 centimeter inverse. RH NH36 3 plus, it have the delta O 34,000 centimeter inverse, and iridium NH36 3 plus, it have the 41,000 centimeter inverse. That means the 10 dq value affect if the position of the metal will be changes. First transition row elements have the lower 10 dq than the second row elements, and second row elements have the lower 10 dq value than the third row elements. That means the third row element can show the highest 10 dq or the splitting of the d orbital. In short, it follows that the value of 10 dq increase with as we go down the group or from first to second, second to third row transition elements. The d orbital splitting are in the order 3d is less than 4d, 4d is less than 5d. The increase about 40 to 50% from 3d to 4d and 20 to 30% from 4d to 5d ions in a period. However, the 10 dq value do not change much. See, the table will be shows the variation in the particularly transmitted light and the wave function pair of the light, the color of the transmitted light is complementary to that which it is absorbed by the complex, and we having the color which will be get absorbed. The transmitted color will be the color of the complex. See, there is the particularly wave number of the absorbed light, and particularly color absorbed light and color transmitted light. If it absorbed the violet, it transmitted the yellow green, and the complex appears yellow green. If blue is absorbed, it transmitted yellow light, complex appears yellow. Green blue, if absorbed, it transmitted orange, compound color of the compound is orange. Blue green is absorbed, then it transmitted red, red is the color of the complex. If green is absorbed, it transmitted purple, and purple is the color of the complex. Yellow green is absorbed, it transmitted violet light, violet is the color of the complex. Yellow light is absorbed, it transmitted blue, appearance of the compound is blue. Orange color light is absorbed, it transmitted blue green color, blue green is the color of the compound. If red is absorbed, if it transmitted blue green, and it is the color of the compound. CFT and magnetic properties of the complex metal complexes. One of the earliest application of the CFT is to explain the magnetic properties of transition metal compounds. This application has been developed to a very great extent, although many refinements are necessary beyond the simple theory to explain the wealth of information availability. In the simple theory, it is the value of 10 dq or delta O and the electron pairing energy which determines the magnetic properties. If the crystal field is strong, electron pairing takes place to the maximum possible extent, and then the complex may show diamagnetic. For example, there is the case of FeCN6 4- ion. If the crystal field is weak, no electron pairing takes place, and the complex may shows the paramagnetism. For example, this is the case of FeH2O6 2+ 3+ ion with 4 unpaired electrons. In going to the second and third transition series, it is expected that the spin pairing will be much more common because 10 dq is 5 to 100% larger in the later series, and also because the spin pairing energy becomes less. The latter effect is partly due to the extension in space of the 4d and 5d orbitals, which is larger than that for the 3d. Accordingly, it is expected that low spin complexes will be formed by heavier transition metals. These and such order observations lead to the prediction of magnetic properties of the complex. With the help of CFT, we can find the number of unpaired electrons, if any, in the given complex, and consequently the magnetic properties. For example, magnetic moment of the complex can be determined or predicted by using the spin only formula. Magnetic moment mu is equal to under root n in bracket n+2 bm Bohr magneton, where n is the number of unpaired electrons. Depending on the number of unpaired electrons, with the help of this formula, we can calculate the magnetic moment of the said complex. The mu value come put to be 1.73, 2.83, 3.87, 4.90, 5.92 for 1 to 5 unpaired electrons. There is fairly good agreement between the expected and observed values of magnetic moment due to the unpaired electrons, beside the correlation between magnetic property and the number of unpaired electrons. CFT can explain temperature dependent paramagnetism. The explanation offered by CFT to explain the magnetic behavior of the complexes of transition metals is one of its greatest advantage over the valence bond theory.